Okay, welcome back to the Mathematical Sciences lecture on Unlocking Victory, Mastering Games Through the Power of Optimization Models. So a little bit of background check. Professor Yan Zhenzhen received her PhD in Management Science from the National University of Singapore, as well as her bachelor's and master's in Management Science, Operations Research in the National University of Defense and Technology in China. Her research interests mainly focuses on the interplay between optimization and data analytics, with applications to various resource allocation problems. I'll hand it over to her to conduct her mock lecture.
Okay, thank you. Thank you for the nice introduction, and very welcome to all of you and to come to my mock lecture. So please scan this QR code just in case you want to raise your hand and you are too shy to speak out during the lecture. And also, sometimes you can try to answer your questions in the Slido. Okay? So today, I'm going to introduce you the optimization model and showcase how to build this optimization model to unlock the victory in playing the game. Okay? So at the very first beginning, let me try to use a simple example to introduce you to an optimization model. So I believe many of you have played the Lego game before. Suppose you have two types of Lego bricks, and one big brick and the other big brick. You have 40 pieces of the big bricks and 120 pieces of the small bricks. Okay? Now, you try to make use of those bricks to produce two products. One product is the chair, which is made of one big brick and 4 small bricks. Okay? The other type of the product is table. So one table is made of 2 big bricks and 3 small bricks. Okay? Suppose you can sell each chair at the price of $40 and each table at the price of $50. Then the decision you're going to make is to determine how many chairs and tables to produce in order to maximize the total revenue. Okay? Is this problem clear? Okay, could you share with me what is your answer if you are going to solve this problem, and what would you like to produce? How many chairs and tables do you want to produce, and what is your revenue? So you can key in your answer how many chairs and tables to produce and what is your revenue. And just to recap, okay, this table summarizes all the information we have so far. That means we have 40 big bricks and 120 small bricks. And producing one chair will consume 1 big brick, 4 small bricks. And producing one table will consume 2 big bricks and 3 small bricks. And we also list the price of each table and the chair in this row. Given all those information, could you? I don't get it. Okay, is it? Let me try to provide again. Okay, make sure you understand the question clearly. So we have 40 big bricks and 120 small bricks, right? Now you try to make use of those bricks to produce chair and table. And to produce one chair, you need to use 1 big brick and 4 small bricks. Okay? And to produce one table, you need to use 2 big bricks and 3 small bricks. So suppose, let me propose one quantity. If I only produce 1 chair and 1 table, then the total revenue earned will be $90, right? And you will not violate this constraint, you will not use up all those bricks available. And then this is possible to produce 1 chair and 1 table. Okay, I see some others. So if I produce 10 tables, 20 chairs, 20 chairs, 10 tables. Okay, 30 chairs and 5 tables. Okay, now we have so many different options, right? So a very intuitive way is we can check those options and to see this production plan will violate any of the constraints or not. That is to check whether it is feasible to produce to generate this production plan. And then among all those feasible production plans, we can compare those profits and to see which one will help you to generate the largest revenue. So this is one possible way. Regarding you check, you just use your eyeball to think about, okay, how many chairs to produce and how many tables to produce, and then just check whether it will satisfy all those constraints, and finally to compare which one will give you the largest revenue. This is one very intuitive approach, right? And now, let's try to formally formulate this decision-making process. Because this is a decision-making process, right? We are required to make some decision. In this case, it is clear we need to determine how many chairs and tables to produce. And then we can use 2 variables to encode these 2 decisions. Use xc to denote the number of the chairs to produce, and xt to denote the number of tables to produce. Okay? So with this production plan, we must have some goal to achieve in this decision-making process, right? You make such production plan in order to maximize the revenue generated, right? Clear? So then the key is we need to formulate this objective using the decision variable we have introduced in the first step. Because in the first step, we already introduced 2 variables, xc and xt, to encode the number of the chairs and the tables to produce. Now, we hope to also provide a mathematical representation of this objective in the decision-making process using those variables. Okay? So we know that the price of the chair is 40 and the price of the table is 50. Then producing xc units of chair will generate the revenue of 40 times xc, right? And producing xt units of table will generate a revenue of $50. 50 times xt. So in total, if you decide to produce xc units of chairs and xt units of tables, the total revenue generated from this production plan should be 40 times xc plus 50 times xt, right? Is it clear? Very good. Now our goal is try to maximize this function. Okay? Then the question is, can we produce as many chairs, as many tables as we wish? Is it possible? No. Why? Yeah, because producing those chairs and tables need to consume some of the bricks, right? And we only have limited number of the big bricks and the small bricks available. So that comes to the constraint part. That means you cannot produce as many chairs as possible because you only have limited resource for you to conduct this production plan. Right? So the simple constraint is when you consume those bricks by producing these chairs and the tables, the total consumption of those bricks cannot exceed the total available bricks. Right? Intuitive? Very good. Now, let me take the big brick as an example. So we know producing one chair will consume one big brick, and producing one table will consume two big bricks. Then producing XC number of the chairs and XT number of tables will consume 1 times XC plus 2 times XT in total, right? That is the total consumption of big bricks when producing XC number of the chairs and XT number of tables, right? And this total consumption of big bricks should be smaller or equal to the total number of the bricks available, which is 40. That comes to our first constraint. Similarly, we can also write down the second constraint that is regarding the limited resource for these small bricks. Clear? So these two are two main constraints we have in restricting us to produce as many chairs, as many tables as possible. In addition to that, what else constraints do we need to have? Can I produce negative chairs? No, right? So the implicit constraint we also need to consider is the non-negativity constraint. You cannot produce negative amount of the chairs and the tables, right? Okay, now in this decision process, we already figure out what are the decisions to make and what is our objective to achieve and what are the constraints in making those production plans. And this, with an optimization model, with decisions, objective, and all the constraints, they are all represented in terms of the decision variables. We call it is an optimization model. Okay? Then we can see we can easily use many of the solvers to solve this optimization model. In this example, we have already some of the proposal, right? Now let me demonstrate you how we can build on some of the open source solver to easily solve this optimization model. Okay? So I have chosen to use this PULP, which is a open source software written in Python. And then this PULP can call many solvers to solve a linear program, to solve an optimization model. And in this example, I have called it CBC, which is also an open source solver. And then let me try to show you some of the code. So this one is tries to demo you. Firstly, you can name your problem and let know this problem is a Lego optimization problem. And then your objective is try to maximize something. This is a maximization problem. And then you can define your decision variables and define your objective function, define your constraints. Okay? All those programming model, you see, is very much like our optimization model. By simply coding those optimization model in this Python, and then you ask the solver to solve this problem. Okay? Then see? This solver can immediately tell you what is the optimal solution. This optimal solution is that we can produce 24 number of the chairs and 8 number of the tables. And this production plan will generate a revenue of $1,360. You can compare this production plan with all the previous proposed plan by all of you. You can see how many improvements you can achieve using this optimization model. Okay? So now, let's try to summarize the steps in solving this Lego game. So basically, this is a decision-making process, right? So in formulating a decision-making process as an optimization model, we should identify what are the decisions involved in this decision-making process and use some of the variable to encode those decisions. That is defined as the decision variable. And based on this decision variable, we can try to formulate our objective, because this is optimization. You must have some objective to optimize in this process, right? Then you try to write down your objective function in terms of those decision variables you have introduced before. And finally, you need to identify all those constraints. Some constraints are explicit constraints, such as a resource limitation constraint. Some constraints are implicit, such as the non-negativity constraint. You cannot produce negative amount of the chairs and tables, right? And then finally, you put them all together. It is a well-defined optimization model. And you put them in the solver, and many of the optimization problems can be easily solved in seconds. And among those optimization models, there is a very special one. It's called the linear program. So this linear program is a special type of the optimization model with the objective function be a linear function in terms of all the decision variables you have introduced. And if, in addition, all the constraints are all linear equations or linear inequalities in terms of the decision variables, and then we can call this optimization model as a linear program. Linear program means everything has to be linear in terms of the decision variable you have introduced. And then in the previous example, maybe some of you may raise the concern, hey, Prof, you cannot produce 2.5 chairs, right? Now, implicit says that, okay, those decision variables might be integer variable. Integer means that you can only take a value of 1, 2, 3, 4, 5. It cannot be 2.2, 2.3, right? So if some of the decision variables are required to be integer variable, then by all the rest of the constraints are linear, and objective function is still linear, and this corresponding optimization is defined as a mixed integer linear program. So from the computational point of view, solving a mixed integer linear program is much more computationally expensive compared to solving a linear program. That's why, in practice, this MIP is less favored. But in some of the applications, it is necessary and very helpful to introduce some of the integer variable. One example is this Gale-Butter-Can switch game. Have you played this before? Before coming to this lecture, there is this game in the atrium, right? You played this before, very good. Then, for those who are not familiar with the game, let me try to recap the rule of this game. So the game rule is very straightforward. That is, you can choose to switch any rows and any columns, okay? But whenever you decide to switch a row, all the lights in the corresponding row will change the status. If it is originally off, then it will be on. If it is originally on, it will be off, right? Similarly, if you decide to switch a column, and all the lights in this column will change accordingly. And to win the game, you are supposed to turn off as many lights as possible. Okay? So since some of you already played the game, can I know how many lights remain on from your switch alternative? For those who have played the game, how many lights remain on from your switch alternative? And particularly, if you have played this big puzzle, SPMS big puzzle, puzzle 11101. Okay? You see this is the SPMS. Yeah, so this one, this is the puzzle, and then we have 58 knights on. Okay? Who has played this puzzle? Okay, can you show me how many knights you can remain on from your switch plan?
I actually got the correct answer. I used 29.
29. Very good. You already get a 29. Very good. You solve it using what approach? What strategy?
I did one by luck.
Okay. Okay. Very good.
I denoted, first I eliminated I made those rows that have most, then there's one, the most suitable lines are the center cross.
Uh-huh.
So I will switch both of them on first. So there's a lot of rows that specifically have a lot of on lines. So you can switch them on. All those that have off lines, yeah, then those will both on, then you can off them. So it's like, if you configure such that without affecting the others, that the row has the most number of lines, then you can off it completely.
Very smart. So how long have you taken to solve this puzzle? How long? 30 seconds. Wow, you are super smart. Okay, so now let's try to see how we can rely on the optimization model we have just learned to solve this game, to win the prize. Okay? So before analyzing this winning strategy, what we need to know is what kind of information we have in playing the game. That is basically the input data in this decision-making process, right? We can observe all the knights' initial status. Okay? And then let me use a parameter Cij to encode this light's initial state in each of the cell ij. The cell ij is the intersection point of row I and column j. And specifically, if the light in cell ij is on, then we ask this Cij be 1. Otherwise, we set this Cij 0. Okay? And then the decision to make in playing the game is you need to determine which rows and which columns to switch. Right? And you can make this decision process, you can make this decision in such a process. That is, you look at each of the row and to determine whether you want to switch this row or not. Okay? And then we can use a binary variable to encode this decision. Specifically, this binary variable means that it can only take 2 possible values, 0 or 1. If you decide to switch row I, then this xi take the value of 1. Otherwise, this xi take the value of 0. And similarly, you can go through each of the columns and to determine whether you would like to switch each of the column or not. We can use another set of the binary variable yj to encode this decision. Yj equals to 1 if you decide to switch column j. Otherwise, yj equal to 0. Okay? So with this decision variable, the next step we can do is we try to formulate our objective using those introduced decision variable xi and yj, right? And what is our objective? We try to win the game, right? According to the winning criterion, we try to achieve the minimum number of the lights that is on. And to do so, we first need to analyze what contributes to the lights that is on in the end. Right? Okay, so let me try to use a simple example to illustrate what contributes to the lights that is on. Suppose I have a light in this cell which is initially on. Okay? And then my action does not change the status of the light. And then this light will remain on in the end, right? The second possible scenario is if the initial status of the light in this cell is off, and I take some action by switching some of the row and the column to change the status of the light. And then it will be on in the end, right? In other words, the final state of the light depends on the initial status of the light as well as your action. Clear? Very good. Now, we know that the initial state of the light can be indicated by Cij we have introduced before, which is the input data, right? Now, to formulate this objective, it is necessary for us to introduce another set of the variable to keep track of whether the status of each light is changed or not, right? And then we use this Hij, another set of the binary variable to keep track of this status change. This Hij equal to 1 if the light in cell ij is changed. Otherwise, I set this value to 0. Okay? Okay, then with this introduced the binary variable, now we are ready to represent this objective in a mathematical function. Our goal is try to minimize the number of the lights that is on, and then with those input data Cij and introduce the decision variable Hij, we can represent the number of the lights that is on as this linear function in terms of H. As analyzed before, this number of lights that is on should include two parts. The first part includes all the lights that is initially on, and your action does not change the status. And the second part includes all the lights that is initially off, and your action does change the status of the light. Clear? Okay. Now, to conclude this optimization process, we further need to formulate its constraints, right? Do we have any constraints in this optimization process? What kind of constraint? Are you limited? I will ask you to try those in the limited times. You can try to switch any rows and any columns as many times as possible, right? It seems there is no clear constraints in this decision-making process. However, remember that we have introduced an auxiliary set of the decision variable Hij to facilitate the formulation of our objective. And we know that this Hij is to keep track of whether the status gets changed or not. This is affected by our decision, our action, right? So then we need to explicitly impose such an inference in the constraints to clearly state how those Hij is affected by our decision xi and yj. This comes to the constraint of this optimization model. Okay, very good. So then we try to use another example to illustrate the rationale behind. So suppose I have a light that is initially off in this cell, okay? And then if you determine to switch row I and do nothing to this column J, and this light will change to be on, which is initially off, now it's changed to on, right? Alternatively, you can also decide to switch column J, but do nothing to row I. This action will also change the status of the light in this cell from off to on. Right? Very good. But on the other hand, if you switch both row I and column j, what happens? If you switch both row I and column j, and the light states will change from off to on, and then from on to off, in the end, it remains unchanged, right? Clear? If you switch both of them, then the light states will remain unchanged in the end. Alternatively, if you do nothing to row I and column j, and again, the light status will remain unchanged in the end. Okay? So to summarize all those findings, so we can see as long as you take the same action for the row and the column, then the corresponding cell, which is the intersection point of this row and this column, will remain unchanged. But if you take different action, you switch one row and do nothing for the column, and it will change the status of the light. How can we encode this relationship using the mathematical form? Very good. Using this Hij equals to the absolute value of the difference between xi and the yj. Right? This specific function tells us as long as xi and the yj take the same value, this Hij will be 0, which means the status will not change. Otherwise, this Hij will be 1, which means you have changed the status of the light in this cell. Okay? Okay, very good. But unfortunately, we mentioned that so far we only focus on the mixed integer linear program. We hope all the objective, we hope all the constraints, they are all linear in terms of the decision variable. But here, this absolute value is unfortunately a nonlinear function. Now, how can we model a mixed integer linear program? We need to figure out some approach to linearize this nonlinear function, right? So in fact, we can show this nonlinear function can be equivalently formulated as a set of linear constraints. Before trying to understand why this statement is true, let's first need to understand what is stated in this claim. Okay? So we first look at this constraint A, B, C, and D. And we realize that, yes, indeed, they are a set of linear constraints, right? Because they are linear inequalities in terms of the decision variable xi, yj, and hij. All the functions involved are all linear. This is nice, right? And here we'll further introduce this auxiliary binary variable zij. Again, binary variable means that you can only take two possible values, 0 or 1. Okay? So this equivalent formulation means what? It means that the possible value for xi and the yj and the hij restricted from this set of constraints must satisfy this nonlinear function. This is what I mean by equivalent formulation, because the set of constraints has restricted the possible value of xi, yj, and hij. And for all those possible values of xi, yj, and hij, they must satisfy this nonlinear function. This is what is stated in this claim. Then is this claim clear to all of you? Okay, if the statement itself is clear, and let's try to proceed to prove why this statement is correct. Okay? So from our understanding of the statement, we know that the key is we try to enumerate all the possible values of xi and yj and hij to see whether they will satisfy the nonlinear function or not, right? Then, what is the possible value of xi minus yj? We note both xi and yj, they are binary variable, right? That means the possible values for xi and yj are 0 or 1. Then the difference of these two binary variables can only take the value of -1, 0, or 1, right? If xi and yj take the same value, then this difference is 0. If xi is 1, yj is 0, and the difference is 1. If xi is 0 and yj is 1, then the difference is -1. So you see, the only possible values for this difference is -1, 0, or 1. And let's try to decompose into two possible cases. If xi minus yj is non-negative, that means it takes the value of either 1 or 0. Okay? And let's try to see constraint C in the set of the constraint we have in the statement. From this constraint, can you tell me what's the possible value of this zij? We know zij is a binary variable. That means the possible value for zij is 0 or 1, right? And with this constraint and the condition xi minus yj is non-negative, what is the possible value for zij? Can anybody tell me? So you see, xi minus yj is non-negative. That means xi minus yj plus 1 should be at least 1. Very good. Then, what is the right-hand side of the constraint? Since zij can only be 0 or 1, if zij is 0 and the right-hand side is 2, because 2 times 1, right? If zij is 1, then the right-hand side is 0, right? Very good. In order to have this constraint hold, we have only possible value of zij is 0. Right? And then if zij is 0, we can further call this constraint A and B to see. Constraint A implies hij has to be less or equal to xi minus yj. And constraint B says hij has to be at least xi minus yj. So the intersection of these two constraints implies that, or in this case, hij can only be equal to xi minus yj. Right? Clear? So this is regarding the first possible case where xi minus yj is non-negative. Then we still have one possibility, right? I can have xi minus yj equals to -1. Okay? If xi minus yj is -1, and we can call this constraint D. So xi minus yj is -1. That means yj minus xi is 1, right? So constraint D says hij must be at least 1. But we know hij is a binary variable. So the only possible value for hij is 1. So now we have enumerated all the possible values for xi, yj, and hij, right? Okay. Indeed, we find that hij always equal to the absolute value of xi minus yj. For the first case, when xi minus yj, which is non-negative, hij equals to this difference itself. But in the second case, if this difference is negative, which means that it takes the value of -1, and hij equals to 1, which is the negative of the negative, which is 1. So now we have convinced that, okay, yes, indeed, we can reformulate the set of the nonlinear constraint in this linear form, which leads to this elegant mixed integer linear program. So you see, objective constraints, they are all linear in terms of decision variables. In fact, all the decision variables in this program are all binaries. Clear? Now, with this mixed integer linear program, let's try to revisit this big puzzle. This SPMS puzzle? Okay? Then let me show you how to use this Python PULP to solve this puzzle. Okay? I first input the data in this. So the data is to specify how many what cells the light is on. Okay? So this is the data, input data we have. And then the next one is we need to encode our optimization model in this Python programming language. So by specifying this is a minimization problem because we try to minimize the number of lights that is on. And then you need to define your decision variable. We have 4 types of the decision variable, H, X, Y, Z. And this C is the data we have, right? The input parameter, which specify the initial status of the light. Then we formulate our objective function, and then write down all the code, or all the constraints. Then solve this optimization problem. Okay? Now let's see what is the results. Okay. Yeah, it finished. So within seconds, we can find what should be the switch plan. This one says you should switch row 1 and row 7 and column 1. So I already visualized this solution in these slides. So this is the switch plan suggested by this optimization model. That is to switch row 1, row 3, row 7, column 1, column 3, column 5, and column 7. And this switch plan will only have 29 lights on. That is the optimal solution. Congrats to both of you. Clear? So you see, many of the optimization problems, many of the puzzles, including the Sudoku, can be easily solved within seconds used by building this optimization model. But today, I don't have time to show you the details. But if you are interested, I can pass the model as well as my code to you for you to try different Sudoku game. Okay? So before ending this lecture, I want to basically convince you that we can do a lot of applications with this mixed integer linear program. These slides showcase some of the projects I have done. So the first one is you can definitely build this mixed integer linear program to solve various games, including the Sudoku game, okay? And also, you can build this optimization model and to optimize the satellite scheduling problem. This is one of the projects I have done during my master. And then you can also build a mixed integer linear program to optimize the price for the company to help them maximize their revenue. You can also, this is the consulting project done for the McDonald's. And this one, I don't know whether it looks familiar to you or not. It's essentially our Singapore map, right? It is the last mile problem I have done for the company. So again, by building the mixed integer linear program, you can solve this last mile problem for this logistics company. And finally, is the supply chain risk mitigation. So again, by building this mixed integer linear program, you can solve this inventory management problem to mitigate the risk from this supply chain. Okay? So by attending this optimization course, I believe that you'll be convinced the power and the beauty of the optimization model in solving many of the real applications. Okay? So any questions regarding the lecture? Yes?
Actually, when you model the bivariate variable,
Yes.
is it possible to use using modulo 2 to determine HIJ?
Oh, this one is essentially, the binary variable is already make use of this modular tool. It can only take value of 0, 1. So that the reason I guess you are saying the modular is because when, let's say if you can switch in the same row for multiple times, right? And it is equivalent to just switch this row once or just do not switch your row. If you switch your rows all number of times, that means it is equivalent to you just switch your row once. And if you switch your row even a number of times, that means you don't switch your row. So we already did this analysis before playing the game. That's why, in the end, we find that it is sufficient to only introduce this binary variable. Yeah, good. Any other questions? And if no, thank you all for attending my lecture. See you.
Okay, here's a fun fact about whatever you just heard in all the concepts being taught. It's actually in a module called Basic Optimization. I'm actually taking it right now. And it's actually pretty cool. It's pretty elegant, and you'll learn a lot of stuff. It's actually a module in Applied, so if you want to do Applied as your track, well, you're going to see her probably. So yeah. Okay, so unfortunately, we have actually come to the end of all our talks and panel and all that stuff. If you have any more questions, feel free to engage our faculty members, students, as well as alumni at the atrium on level 3. And we also have our Telegram channels. Let me just reiterate that. It's called NTU Math and Physics. That's an underscore, by the way, if you cannot see. Transport information, if you want to head back to the School of Biological Sciences, you can actually take the bus from our lobby at level 1, where all the other NTU open house booths are is at SBS. There are also shuttle buses from the School of Biological Sciences that will take you back all the way to Jurong East MRT. Or if you want to leave from here, from SPMS, just take bus service 179. It will take you to Boon Lay or Pioneer. So announcements, we would love to hear for your feedback for all of our events for today. Please scan the QR code right above me. If you want to submit one, you actually have a chance to win a $10 voucher. Wow, okay. We hope that you enjoyed your day here at SPMS or overall at NTU for open house this year. And we hope to see you around, maybe as freshmen in a couple of months. This is Sharifa signing off. And if you have any questions for me, maybe, you can come on down here. I'm happy to answer any.